So let us look at the case of two particles or two bodies scattering off each other by some kind of contact interaction in a very short time as an example of the application of the conservation principles of conservation of momentum and conservation of energy to see whether we can understand this scattering process to the extent we can without detailed dynamics. And it turns out that we can practically we can go a great distance using just the conservation principles. As I started saying, in the first case, let us look at the simpler instance when you have a target particle. This is the target of mass m2 and a projectile coming in of mass m1. So this is the projectile and that is the target, and the projectile comes in with some momentum p1 directed in this to the right, and after the collision you have a particle 1 moving with some momentum p1 prime and 2 moving with some momentum p2 prime, and it is possible that p1 prime is positive as well. The particle pushes this along and moves with a different momentum in the same line, and that would show up if p1 prime is positive, but it is intuitively clear that if m2 is much heavier than p1 than m1, this particle is likely to recoil after hitting it and give a small amount of momentum to the particle m2. So let us quantitatively write this down. Conservation of momentum implies that the initial momentum should be equal to the final momentum. So p1 prime is p1 is p1 prime plus p2 prime, the algebraic sum of the two, and I do not need to put vector signs in this case because it is the one dimensional case. Everything is moving along a given line, say the x axis. The conservation of energy, on the other hand, would imply that the total initial kinetic energy should be equal to the total final kinetic energy. There is no loss of energy anywhere in this elastic collision. So this is because elastic collision, and the initial kinetic energy of course is p1 squared over 2 m1, and that should be equal to p1 prime squared over 2 m1 plus p2 prime squared over 2 m2. So we have two equations for two unknowns given p1, and of course the masses of the particles, the parameters m1 and m2 are supposed to be given to you, and you are given the value of this variable p1, and you need to find p1 prime and p2 prime. Actually, just using dimensional analysis, it is immediately clear that the only quantity of dimensions momentum that you have here is p1. So it is immediately clear that p1 prime and p2 prime must be proportional to p1. They can't be proportional to anything else. They can't be proportional to the speed of light, for example, because this is non-relativistic physics. The only quantity that you are given of dimensions momentum is p1, and therefore p1 prime and p2 prime should be proportional to p1 directly. We can make that statement immediately. But let us see how this is borne out from these two equations. Multiplying through by m1 m2 or something like that, you discover that p1 squared minus p1 prime squared, I subtract this, multiplied by m2 times this is equal to m1 times p1 p2 prime squared. On the other hand, we also know that p1 minus p1 prime is equal to p2 prime. So dividing this by this and cancelling out p1 minus p1 prime, we have m2 p1 plus p1 prime is equal to m1 p2 prime. So we have two simultaneous equations in two unknowns. We have made them linear equations now, and one of them is m2 p1 prime. So let's work this out. Minus m1 p2 prime is equal to, bringing this to this side, taking this across, is minus m2 p1, and we also have the original equation, which is p1 prime plus p2 prime equal to p1 on the right hand side. So there are two simultaneous equations for which the solutions are easy to write down. P1 prime therefore is equal to minus m2 p1 p1, these are the inhomogeneous terms, and then the coefficients here are minus m1 and 1. This divided by the determinant of coefficients here, which is m2 minus m1, 1 and 1. So that immediately gives us m1 minus m2 here times p1 divided by the determinant is m1 plus m2, and that's the solution for p1 prime, which is intuitively very satisfying, because it says that if the masses are equal, if this mass is equal to this mass, then we know already that if this comes along with a certain velocity, all it does after the elastic collision is to give this particle that velocity and stay at rest. This is how Newton's cradle works, for instance, for equal masses. So it immediately tells you that you're on the right track. It also tells you that if m1 is bigger than m2, then p1 prime is positive, which is what you expect. If this is heavier than that, if there's more massive than that particle and this is at rest, when this comes along and hits it, it's clear that this particle is going to continue to move in the same direction, which means p1 prime is positive. On the other hand, if m1 is less than m2, then p1 prime is negative. It says if you have a lighter mass here and a heavier mass here and you go and hit it, you're going to recoil backwards here, which is exactly what's happening there. So this looks like it's a very, it immediately tells you this solution is on the right track. What about p2 prime? Well, that's equally easily written down. We have the same equations. So that's solution number 1. P1 prime is this thing here. And what's P2 prime? P2 prime, this is what the target momentum, the momentum the target acquires after the collision. And that's again equal to, the coefficient here is m2, it's 1. And here we have minus m2 p1 and then p1 divided by the same determinant, which is m1 plus m2, and this time it's equal to m2 p1 plus m2 p1. So it says p2 prime, and let me write it next to this. P2 prime is equal to twice m2 p1 divided by m1 plus m2. So that solves the kinematic problem completely. It tells you, regardless of the details of the interaction between these two particles when they are in contact, if that happens in a very short time, then after the collision, when these particles move off as free particles, particle 1 moves with this momentum, particle 2 moves with this momentum. This is the momentum acquired by the target after the collision. Again, you see that P1 prime and P2 prime are proportional to P1, exactly as we expected on dimensional grounds, because these are dimensionless ratios, the ratios of masses, and then you have a P1 here and a P1 there. So this completes the solution in some sense of this simple one-dimensional problem. We can actually extract some useful information from it. Incidentally, notice again that in this problem, if it should so happen that if m1 equal to m2, then P1 prime is equal to 0 and P2 prime equal to P1. In other words, this numerator to denominator cancels out and you get just P1. So there's exchange of momentum. The projectile's momentum is transferred completely to the target, and the target moves along and the projectile remains at rest. That's what you expect for equal masses. And as I said earlier, if it should so happen that m1 is less than m2, then there is a recoil backwards of the projectile while the target moves a little bit forward in the forward direction. What's interesting is to ask, what is the amount of energy transferred in this process to the target? How efficient is it to transfer energy from the projectile to the target by giving the initial projectile a certain amount of energy? Well, we know that the energy transferred, energy E transfer, is equal to P2 prime squared over 2m2, because the initial kinetic energy of the target was 0 and now it's acquired the amount of energy P2 prime squared over 2m2. So that's the amount of energy transferred from the projectile's initial state to its final state. The difference between the two is precisely this quantity. But what is that equal to? That works out to twice m2 P1 squared over m1 plus m2 the whole squared over 2m2. So this is equal to twice m2 P1 squared over m1 plus m2 the whole squared. Now what we'd like to do is to compare it with what the initial kinetic energy was, which is of course P1 squared over 2m1. So let me write this relation in the following way. Let me write this as E transferred is equal to P1 squared over 2m1, that's the initial kinetic energy. So I divide by 2m1 and multiply through by it, and then up there you get times 4m1 m2 divided by m1 plus m2 the whole squared. But this is equal to E initial, that's the initial energy, times 4m1 m2 over m1 plus m2 the whole squared. So it's this ratio here, that quantity, which tells you how efficiently this energy transfer is taking place. And look at what's happening. It's quadratic in the two masses here. So all that it's the relevant parameter here is not the individual masses at all, but rather the ratio of masses. So let's introduce a quantity which is the ratio of these two masses. So let R equal to the mass of the projectile to the mass of the target, which is of course m1 divided by m2. Then our relation here, the fundamental relation, says the energy transferred is equal to the initial energy multiplied by, I pull out an m1 here or an m2 here and write this as m1 divided by m2. So if I do that, this is equal to 4r divided by 1 plus r the whole squared times E initial. So in terms of this ratio, the energy transferred is this quantity multiplied by the initial energy. So all we have to do is to examine what this quantity looks like for various values of r. R is a ratio of masses and therefore it's non-negative. So let's plot therefore E transferred divided by E initial, this ratio. Let's plot that as a function of r from 0. We need to plot the quantity 4r over 1 plus r squared. Now for very small values of r compared to unity, this is negligible and the answer is 4r. So it starts out like a straight line with slope 4 in this fashion, And then for very large values of r compared to unity, the numerator goes like r, but the denominator has an r squared, and so therefore the ratio goes like 4 divided by r and drops off like 1 over r. So in between it must have a maximum at some point and drops off in this fashion, and it is obvious on inspection or differentiation that the maximum occurs when r is equal to 1. When r is 1, the numerator is 4, the denominator is 4, and the ratio is 1. So you have complete transfer of energy at the point 1, and this is 1. And this is the situation when m1 equal to m2. As we saw already, when the masses are equal, when the projectile has the same mass as the target, it transfers all its energy to the target, and the target goes off with the full amount of initial energy. So therefore, you have efficient transfer of energy as long as m1 is comparable to m2. If it is much smaller, the energy transfer is very small. If it is much larger, it is again very small on this side. So it immediately tells you the best way, the most efficient way, purely using kinematics, conservation of energy and momentum and nothing more than that, is if the projectile and target masses are approximately equal to each other, and then you have very efficient energy transfer. So we have arrived at this conclusion without too much input, just the input of these conservation laws. Now let us see what the more general case is. So let us look at the general case of scattering of two particles, but we can again do the same thing. We can again say that the target is at rest, so that is the target, mass m2, and along comes m1, mass m1, with initial momentum p1, a vector now. What happens after scattering? Well, here comes the initial vector, and one particle goes off in one direction, the other part goes off in some other direction altogether. So if after collision with respect to the initial direction, you have the projectile going off like this with momentum p1 prime, and the other particle going off like this, the target going off like this with momentum p2 prime. P1 prime and P2 prime form a plane, and conservation of momentum now tells you, implies that P1 is equal to P1 prime plus P2 prime as vectors, as three-dimensional or any-dimensional vectors in dimensions greater than 1. But these two form a plane, and this relation tells you it is a linear combination of these two vectors, and therefore is in the same plane, and without loss of generality I take that to be the plane of the blackboard. So this is really a three-dimensional collision problem, if you like, but this is what it reduces to. And then with respect to the initial direction of P1, let us suppose this moves at some angle alpha and that moves at some angle beta measured from the x-axis downwards in this case. So that is the general geometry. P1 is P1 prime plus P2 prime, and we have now got to impose this conservation of momentum in terms of components along the initial direction and perpendicular to it, and we also have the conservation of energy. So let us write these equations down and see where it gets us and what the unknowns are. So resolving these vectors along the direction, incident direction, and using symbols without arrows for the magnitudes, it follows that P1 prime cos alpha plus P2 prime cos beta, the projection of this vector in this direction is like that, and it is P2 cos prime cos beta, and this one is P1 prime cos alpha here, and that must be equal to P1, the initial momentum, P1, magnitude of the initial momentum. Similarly, the vertical projections, this vector has a component upwards, this vector has a component downwards, and taking that minus sign into account, P1 prime sine alpha, that is the upward component, minus P2 prime sine beta is equal to 0, because the initial vector has no vertical component, and therefore I put 0 on the right hand side, but this one points downwards, the projection of P2, therefore I put a minus sign here. Okay. So these two imply conservation of momentum right here. The conservation of energy, on the other hand, is a quadratic relation. Conservation of energy implies P1 squared over 2m1 must be equal to P1 prime squared over 2m2 plus P2 prime squared over 2m1 plus 2m2, since the masses are unequal. Where, as I said, I use these symbols without any arrow for the magnitudes of the vector, so they are non-negative quantities. Okay. Now let's take stock. That's it. We don't have any further information. We've used up conservation of momentum, we've used up conservation of energy, and that's all the kinematic information we have from conservation principles. What can we now say beyond this? Well, we have to take stock of how many unknowns there are. There are 4 unknowns. So the unknowns, the known or the given is P1. In fact, the vector P1 is given to you, and we've chosen the vector P1 to be along this direction here. So given that, we need to find the unknowns are P1 prime, the magnitude of particle 1's momentum, P2 prime, the magnitude of particle 2 momentum, alpha and beta. But we have only 3 equations. So we have a situation here which is actually at the root of, it's the beginnings of classical chaos actually, but it turns out that in this problem these 3 do not suffice to solve for these 4 unknowns uniquely. Without further dynamic information on how the interaction took place, what exactly took place in that little time delta t, we cannot say what these quantities are going to be uniquely. All you can say is, given any one of these quantities, we can then deduce what the other quantities are, and then the task of dynamics is to put in further information about the interaction and then predict for various values of any one of these quantities, such as say beta, the angle beta, for given beta, what the other quantities turn out to be. And then actually when you do this problem in terms of quantum mechanics, you would assign probabilities to different values of alpha and beta here and call them scattering cross sections, differential cross sections. But here we are not concerned with that. We are concerned with the geometric problem, the algebra problem of actually finding out what these unknowns are given any one of these quantities, and then we will look through all the possibilities for any one of these quantities and see what results we can get. So what I'm going to do is to assume that we know, so assume that a value of beta is specified. So we will compute the other 3 quantities in terms of a given value of beta, which could run from 0 up to wherever. Now it should be obvious to you by looking at this diagram immediately that once you have a projectile coming in this direction, it is not possible for this mass m2 to go backwards in this direction. At best it should be in the forward half, and therefore it's clear from this already that beta must be less than equal to pi over 2. We can't have it move out here, for instance, but you could have it up to this point here. So that we already know, we have some intuition for this business, and we already know that there must be a limitation on this beta such that it doesn't go beyond this. But given a beta, what are all the other quantities is what we're going to ask, and then we will see what limitations we can put on these angles here. So the task is clear. Given beta, so this is no longer in the list of unknowns, we need to find P1 prime, P2 prime and alpha given these 3 equations with beta and P1 as given, treated as given. So this is the general collision problem for which we are going to try to find a solution. But first, a little bit of simplification of the algebra. Can we erase this? Follows at once, because again you see the only quantity of dimensions momentum is P1 among the given variables. Therefore it's clear immediately from this that P1 prime and P2 prime must be proportional to P1. So let's make life simpler. Let's suppose that let x be equal to P1 prime over P1, and let us put y equal to P2 prime over P1 once again. So it is only the ratios that we are interested in, and similarly this is the only relation where the masses appear, and the masses appear by multiplying through. As you can see, the ratio of m1 over m2 appears here. So it is immediately clear that I could also write r as before equal to m1 over m2 as before. And then what do these equations look like? Well, they simplify quite a bit. So here we are, we have this first equation, this equation here. If I divide through by P1, it says x sine alpha equal to y sine beta. That's the first, this equation is gone. Okay. Then this equation says x cos alpha equal to, I am dividing through by P1, so there is a 1 on the right hand side, right? And then this becomes minus y cos beta. That takes care of this equation. And what does this equation give you? It says P1 squared, I divide by P1 squared all the way through, so let us multiply this, let us multiply through by m1 and remove the 2, so this goes away, and you have plus r out here, and I divide through by P1 squared, so it says x squared plus r times y squared equal to 1. Those are the three equations, and that takes care of all the three equations that we put in. Now for the solutions. So the simplest way to do this, there are many ways of doing this, but the simplest way to do this is to notice that if I square these two fellows, I immediately get x squared, and on the right hand side I get an equation which will tell you. So let's square these, and says x squared is equal to the square of this plus the square of this. The square of this will give me y squared straight away minus 2y cos beta plus 1, which is this term here when I square it. But for x squared I write 1 minus ry squared, so this at once gives you one plus ry squared, this 1 cancels out, 1 plus ry squared is 2y cos beta. Okay. And y is not 0. Y is the magnitude of the second momentum divided by the magnitude P1, and therefore the only solution is y is 2 cos beta over 1 plus r. So we have our first solution. By the way, that solution tells us that beta cannot be greater than pi over 2, because then cos beta is negative, but y is the ratio of the magnitudes of two vectors and cannot be negative. So this automatically says that beta cannot scatter in the backward direction. So it's nice that it's coming out automatically. So once you have that, we can then go on to write down what x is, because we have a solution for y and we use this relation. So it says x squared equal to 1 minus r times y squared, which is equal to 1 minus r times y squared is 4 cos squared beta divided by 1 plus r the whole squared, which is equal to 1 plus r the whole squared multiplied by 1 plus 2r minus 4r cos squared beta plus r squared, and therefore x is equal to the square root of this whole thing, half 1 plus r, this fashion. But we can simplify that a little bit. I can do that by writing this as 1 plus r squared and then a 2r, so it's 1 plus 2r, 1 minus 2 cos squared beta, that's minus cos 2 beta. So this is equal to minus 2r cos 2 beta plus r squared to the power half divided by 1 plus r. Let's see if that's right. So I take out a 2r and I write 1 minus 2 cos squared beta is minus 2 cos beta, cos 2 beta. So that's it. That's the solution for x. And remember that this is x, this is equal to p1 prime divided by p1. On the other hand, this was the solution for y we already wrote down, and this was equal to p2 prime over p2 in this fashion. Yeah. Now we are all set to find alpha 2. So let's do that. From these two equations, the tangent of alpha is immediately found. So these two imply that tangent alpha equal to y sine beta over 1 minus y cosine beta, and this is equal to, again we use the solution for y as 2 cos beta, so you have 2 cos beta sine beta divided by 1 plus r, but that's going to cancel on both sides, and down here you have 1 plus r 1 minus 2 cos beta 2 1 plus r 1 plus r minus 2 cos squared beta, but 1 minus 2 cos squared beta, 2 cos squared beta minus 1 is cos 2 beta, is a factor 2 cos beta sine beta over 1 plus r divided by 1 minus 2 cos squared beta over 1 plus r, this fashion. So therefore tan alpha is equal to 2 cos beta sine beta is sine 2 beta divided by 1 plus r minus 2 cos squared beta. So it's r plus 1 minus 2 cos squared beta. This is equal to sine 2 beta over r minus cos 2 beta. So that's the solution. Okay. Therefore, there's a, and this r, remember, is m1 divided by m2. So there's a simple relation which connects the scattering. Again, to draw the geometry, this was the incident direction. That's the direction of the mass m1, the projectile, and that's the direction of the mass m2, the original target. This angle is beta, that angle is alpha. And we have a solution which tells you what each of these momenta are, p1 prime and p2 prime. We also have a solution for the angle here. So what we need to do is now analyze this solution and see what all the special cases are, and we'll do that next.